Hello and welcome. Welcome back to the lesson 2. It is on sequences, series, and sigma notations. The lesson objectives are to investigate several different types of sequences and to use sigma notation to represent and calculate sums of series. We will come across these both in a while. The keywords of this lesson are sequence, finite sequence, infinite sequence, recursive sequence, explicit sequence, Fibonacci sequence, or Fibonacci, converge, diverge. So there are plenty of these. Let me just quickly glance through few. Finite means it is countable, 1, 3, 5, for example, so many. Whereas infinite will be 1, 3, 5, and dot, dot, dot. Three dots indicate it goes on forever, infinity. Recursive and explicit, we will come across them. Recursive is something, it'll be like a formula where you require the previous term. Say, for example, you have to find A3, the third term. You need to know A1, you need to know A2, and you need to know A3. Only after you know A1, A2, only then you can go to A3. If you want A4, you need to know the previous term. That is about recursive, repeating. Whereas explicit is like a formula where you can directly find any term you want. If I want A4, the n is 4 and directly I put in the formula, I'll get the answer. That's the difference, the general difference between these both. Fibonacci is a beautiful sequence which is usually found in nature. It has been formulated by Fibonacci, I believe, is the scientist's name as well. So it's named after him basically. So he found out in nature there are various patterns, and that sequence is Fibonacci's sequence, and we can find it in numbers, in different patterns and all. We will come across this. Then converging and diverge. Whenever you say converge, it means you're coming close to each other. Two cars are converging. Whereas diverge is going away. They're not coming to a similar point. It's moving away to an indefinite point. So this is basically it. Now about sequences. Finite, we just went through across this. Finite is something that is, countable, whereas infinite is, it goes on with these three dots. And a little bit of this knowledge was, discussed in the previous lesson, the lesson 1 as well. And now we will get into the problems. Find terms of sequences. Find the next four terms of the sequence. 2, 7, 12, 17. We have done this in the last lesson. It's the same one. See the common difference. Is there any common difference? You can see phi is being added all the time. The nth term is not given, so it is infinite sequence, but we know the pattern is basically phi greater than the previous. So d value is phi. So how do you find the next terms? Just keep adding phi. Add phi to 17, it will be 22, plus phi 27, plus phi 32, plus phi 34. That is how we can find the next four terms. Whereas now it is interesting. Find the next four terms of the sequence 2, 5, 10, 17. It is not an arithmetic sequence. It is not even a geometric sequence. See, over here 3 is added, and over here 5. Then over here 7. So what is happening? Let's try dividing. 5 by 2 is 2.5. No. And 17 by 10 is 1.7. No. Sorry for my handwriting. It's 1.7. So it's not a geometric sequence, neither it is an arithmetic sequence. What is it? Let us see carefully over here. We can find a pattern. If you think about this, 2, 5, 9, 17. If you subtract 1 from all this, you will get 1. See, let's minus 1 everywhere. 1, 4, 9, 16. These are all perfect squares, isn't it? Square these. 1 square, 1 square 1 plus 1. It's 2. 2 square plus 1, 5. 3 square is 9 plus 1 is 10. 16 squared plus 1 is 17. Next would be 5 square. 25 square plus 1. So over here it would be 26. So now over here you can see this is the pattern over here. N square, in the sense it starts with 1. So n square plus 1. Now we have 1, 2, 3, 4. Now 5 square plus 1 will be 26. 6 squared is 36 plus 1, 37. 49 plus 1 is 50, 64 plus 1, 8 squared is 64 plus 1 is 65. This is the sequence over here. So these would be the next 4 digits because this is the pattern. Takes quite a while, but if you recognize the numbers, it's easy to find these patterns. Okay, these are about perfect squares. So now, last one in this, you can see over here they have given a formula. Now this could be told as an explicit formula. Why? Because you can put n and you can easily find the numbers or the terms. So for example, the explicit formula is given for an, and n can be 1, 2, 3, 4. Why? Because we need to find the 4 terms. Now substitute n as 1 in this. What is going to happen? A1 will be, the first term will be 2 times 1 into minus 1 the whole power 1. Put it in the calculator. 2 times 1 is 2, minus 1 the power 1 is 1, negative 1 times 2 is minus 2. Same way, use it for n2. You will get the answer over here 4. Just over here, negative 1 squared will be 1, positive 1, 2 times 2 is 4, so it's positive 4. Same way, substitute instead of n 3, and you can solve it simply. Over here now it will be minus 1, so 2 times 3 is 6, but it will be minus. Here it will be positive. Why? Because power 4 means it will be positive 1. You can try it in the calculator, but you can easily solve this even without calculator. So this is the pattern. These are the terms we will get, the next 4 terms. Now the first 4 terms, because we have not been given any terms, so these are the answers: minus 2, 4, minus 6, 8. The next one would be negative, then positive, negative, positive, just put the n values. Now over here, recursively defined sequences. Find the 5th term of the recursively defined sequence. A1 is given as 1. See, look over here. An is an minus 1, means you need to know the previous term and then you need to add the terms to n minus 1. Where n is greater than or equal to 2, you can't start with a1 because a1 is already given. Okay, so you need to start with 2, greater than or equal to 2. So you need to put a2 over here. A2 minus 1 will be a1 plus n is 2, so 2 into 2 minus 1. Put this in calculator, you'll get the answer. You'll see now, it's very simple. You should know what is given. A1 is given. So now we will find for n equals 2. Let's start with n equals 2. We have to start, we can't go behind it. Now, a2 equals a2 minus 1 plus 2 times 2. Instead of n, it's 2 minus 1. Now here, a2 minus 1 will be a1. And 2 times 2 is 4, minus 1 is 3. What is a1? A1 is 1. So just substitute it over here. Okay, I'm sorry, a1 is supposed to be 2. My bad, when I was writing the question, this is 2. I hope this is clear. It is a1, the first value is given as 2. Okay, this is the error in the question. Now it's correct. So a1 is 2. So all you do is substitute the a1. You need to know the initial value a1, only then you can find the next terms. So now with a1 you found a2. Now the answer for a2 is 5. We need 5th term, so use the next term. So a3 will be a3 minus 1 plus 2 times 3 minus 1. Now look over here, what happens? 3 minus 1 means a2. That means we need the second term in order to solve the next term. I mean, we need the previous term in order to solve the current term. So for a3, you need a2. And over here, 2 times 3 is 6, minus 1 is 5. 5 times, what is the previous 5? 5 times 5 is 10. Same way, do it for 4. You need a3 over here. 2 times 4 is 8, minus 1 will be 7. And a3 is 10, 17. Same way, last one, a5. We need a4 value over here. A4 plus 10 minus 1 is 9. So over here, we will have a4 plus 9 or 26. So how do we find this 26? A4 is 17 from the previous term. Just substitute over here. Plus 10 minus 1 is 9. When you add it, you get 26. So now over here, the most important thing, what you must remember is in recursive formula, you need the previous term, only then you can go forward. Whereas explicit formula, you can directly solve for any n value, any term. So I hope this is clear. And in the next sections, we will solve more interesting problems on sequences, series, and different type of patterns.